I am Monica Beckwith, as you mentioned, and I'm going to talk about just a couple of concurrent collectors in OpenJDK. These are the newer ones. And I'm going to try to contrast it with the current default, which is garbage first, garbage collector. As Richard mentioned, I am Java champion, Java 1 rockstar. My knowledge on collectors is primarily because of the performance work that I did on garbage first, garbage collection. And almost all the collectors that I have mentioned here, I have provided links to the articles that I read. Of course, looking at the source code is also a good option. And there are a lot of presentations out there about these collectors, and I have pointed that out in further reading as well. So what I'll try to cover in the next 50 minutes, so trying to talk about 3 different collectors and comparing them and contrasting them is about like 3 talks in itself or more, maybe even when you're trying to compare them. So what I've tried to do is kind of lay the groundwork first. So certain terminologies like regions and collection set and everything, I'll try to cover that first, because this is common for all the collectors I'm covering today. And then I'll talk about individual differences in algorithms for marking and how the compaction copying happens. So you will see this kind of 2 different sets, and then there'll be a transition. So just trying to prepare you for that. So the 3 collectors that I'm covering today, ZGC, Shenandoah, and garbage first, garbage collector, are all regionalized. Okay? So what does that mean? So before regionalized, let me also go talk about Stop the World collection in general, because even when you're regionalized, and the concept is that all these regionalized collectors are copying from one region to the other region. So how does that copying happen? What does it mean when you're saying copying? What are these from in 2 regions? And then we'll talk about regions, okay? Because the flow of the explanation is kind of better that way, okay? So let me go to Stop the World versus concurrent. So when you're thinking of your application threads, they're all working at the same time and doing their chunk of work. For Java, we call them mutator threads, okay? Because we also have the concept of garbage collection threads. And mutator threads are basically the threads that mutate the heap, okay? So now let's look at the Stop the World concept of garbage collection. You have your application threads, and they're, right now, they are filling up your heap, and now there is an object allocation failure, okay? At that time, the garbage collectors need to come in, and so a save point is requested. So because I'm going to talk about ZGC, which does thread local handshakes, I want to introduce the concept of global versus thread local. So how is the save point handled? So it's based on either it's global, which means a single save point request is made and all application threads have to come to a save point, and then the garbage collection work can go on. Thread local means that you have handshake with the threads. So there's a little bit overhead of the handshakes, but each thread can individually come to a save point. So looking at global save point, after the save point was requested, we can see the application threads take their own time to come to a halt. And at that time, the last thread is when your save point gets executed. So this particular gap from the time it was requested to the time it got executed is called the time to save point. It's very important even for concurrent collectors, and I'll show you here soon. Because this is Stop the World, so then once the save points are reached, we do garbage collection execution, which means all garbage collection threads will kick in and start collecting garbage. And I'll explain what that means for each of these collectors. After the GC is completed, your application threads will resume during mutation of the object graph. So, so we covered the thread local. So we covered the global stop the world transition. But what about thread local? So it's the same thing. The application threads keep on allocating. You have object allocation failure. A save point is requested. Okay. So now the applications take their own time to come to a halt. Okay. And then what happens is, because we're doing thread local handshakes, when the application threads come to a halt, there is a phase where there is some work done of handoffs. So you're handing off transition to the GC threads, or you're handing off some kind of your, say, mark stack to the threads. So that is this chunk of orange that I've shown here. Those are called handshakes. And then your application threads can resume, and your GC threads can work concurrently, or GC threads, if it's stop the world, then they will continue from the handshakes onwards. Okay, so basically between a global stop the world and a thread local handshake, you can see the differences. So application threads start resuming work earlier, so it's a shorter kind of pause. So now in thread local's handshakes, I've introduced the concept of concurrent GC. Let's just look at the concurrent GC, how it works along with your application. So you have your application threads. They keep allocating until it cannot allocate anymore. You have a short stop the world pause, and that's called, usually it's initial mark. So your GC threads at that time will do the initial mark. These threads are called parallel GC threads because they work in parallel with each other. And then the application resumes. At that time, you have two GC threads here, and they're called concurrent GC threads because they work along with your application. And then you have other stop the world pauses. You will have your parallel GC threads working during the stop the world pause, and your concurrent GC threads will continue working along with the application threads. Okay, this is what you would see in ZGC and even Shenandoah. You'll see most of the stuff done concurrently. The reason I was differentiating between parallel GC threads and concurrent GC threads is because these are options, these are tunables, and because your concurrent GC threads are working along with your application threads, those counts are lower. Usually it's 1/4 of your parallel GC threads, which are only working by themselves. So you can increase the parallel GC threads to keep the stop the world pauses to a minimum. So let's go to the heap layout now, and let's talk about regionalized heap. Before I introduce regionalized heap, I want to talk about generational. So this is your heap, this is regionalized heap, and this is your heap with generations. So you have young generation and old generation. The idea behind generational heap is that most objects die young. That's the weak generational hypothesis. So prior to Shenandoah and ZGC, I think all the garbage collectors in OpenJDK HotSpot were generational. So objects get allocated into the young generation, objects get aged in the young generation, and then objects get promoted into the old generation. So the idea is that you only promote long-lived objects, and that's basically your live data set. Of course, the generational heap with G1 GC is regionalized as well. So current state is that ZGC and Shenandoah are single generation, and G1 GC is young and old generation, so 2 generations in G1. So let's talk a little bit more about certain common features. So the next concept I want to introduce is compaction, okay? Because G1 GC does compaction, and so do ZGC and Shenandoah, but they do it either in concurrent way, and G1 GC does stop the world. Going back to our heap, we will now divide the heap into from space and to space. So when we're trying to do compaction, you will hear the terms evacuation, you will hear the terms copying. It's basically moving objects from the from space into the to space. The objects that you move are called live objects, and then you can reclaim back the from space. So I'm going to show how that happens. So we have objects in the from space, and your from space gets filled up, okay? At that point, and it doesn't always have to get filled up, but there would be thresholds, basically. Up to a certain threshold, you would say that now I need to start copying the live objects over. So in this particular case, our threshold is filling up the entire from space. So how do we decide what are live objects? So for that, I want to introduce the concept of GC roots. These are basically your thread local variables or references, intern strings, for example, J and I. So here I've taken static variables, your thread stack, and any J and I references. And those are your roots. So from the roots, I start marking any objects that are reachable. And then from the reachable objects, other objects that are reachable in the from space. Once that has been done, that means all the live objects are marked. You have your live object graph ready. And now you're ready to be able to move the live objects into the to space, yes. So we move the live objects into the to space, and then we can reclaim all the from space. For the next collection, the to space is now the from space, and then the from space becomes the to space. So for the next collection, you will be from, again, it's from to, and you're based on your threshold of your from space occupancy. Okay, so that is how a compacting collector or an evacuation or copying collector works. And this is a commonality for all the GCs that I'm covering today. So I did mention about the threshold. So how does that threshold determined, and what does it mean, free regions? So when I spoke about reclaiming back the from space after we have moved the live objects. So in a regionalized garbage collector, we call the reclaimed space free regions. So anything that has any object is called occupied region, and anything that's not occupied is free. So you have your regionalized heap here, and then we have these objects in the from space. So what we say is those are the occupied regions, the ones in green. How would this look in reality? So when I show you these kind of, this nice layout, it seems contiguous, which it is, heap is contiguous, virtual heap is contiguous, but the regions and the occupied regions, for example, do not have to be contiguous. So in real life, it could be something like this, okay? So basically, all these are just regions, and some of them are occupied and some of them are not. So the free regions are maintained in a list, and it's called a list of free regions. In case of generational heap, like G1, you would have the occupied regions could be either young or old regions. There's also the concept of humongous objects, and those will be also like humongous regions. Okay, and then let's see, now that we know occupied and free, and we apply the concept of compaction, right? How do we do that? Remember I mentioned thresholds once we reach a particular occupancy, right? How do we, so once we do reach that occupancy, how do we decide what do we want to move? The primary way that it's decided for all three collectors is regions with the most garbage, okay? So what I've tried to show here are regions, occupied regions in green, and then with the blue highlight, that means they're live, okay? So one of the regions has all their objects are live, or actually a couple of regions have all objects live. So let's look at what regions will collect. So basically regions with the least amount of live objects, right? So at first I already know that these two regions have no live objects, so they're called full of garbage. So they can be reclaimed very quickly. They don't have to wait for compaction to happen. As soon as you identify your liveness of your regions and you're aware that the regions are full of garbage, you can reclaim them. So they can be gone right there. Next, we identify, based on the liveness and the expense of the region, we identify that these two regions have the least amount of live objects. So those are candidate regions for collection. So we'll identify a free region to move them to, and then we'll move the live objects here, and then the two regions that were in the collection set are reclaimed. So the priority is to reclaim regions with the most garbage, as you just saw. I also mentioned something about collection set. So the candidate regions for collection or reclamation are called the collection set. So during every collection cycle, you will have these candidate regions, and those are the only regions that will be collected. This is true for ZGC, Shenandoah, and G1 GC. So there are thresholds. So each of those garbage collectors will have their own thresholds based on how expensive a region is and how quickly you want it to get done. So because we want to do partial incremental compaction, so you would only want to have a particular threshold that you want to do, so based on the time that you want to spend in that. I mentioned incremental compaction. So all three garbage collectors achieve incremental compaction, also known as partial compaction, which means that you are compacting only areas that are least expensive and easier to do. So for example, if you have all live, then you will not do incremental compaction, you will not even touch it. So you will just keep it where it is, so no relocation for expensive regions. So even for incremental compaction, because you're trying to achieve a target, for example, all of these are doing incremental, all of the garbage collectors that I mentioned, they're trying to achieve some latency target. So based on the latency target, you will only do so many regions for choose so many regions for compaction. So, that's called the reclamation threshold. And reclamation stops after the desired threshold is reached. One thing that I want to, so because the concept is the same, it doesn't mean that we have to stop the world for the garbage collection. Yes, it gets very difficult, and that's what I'm going to talk about when I talk about Shenandoah and ZGC, how they do concurrent compaction. But only G1 does stop the world compaction. Both the other GCs do concurrent compaction. So this compaction doesn't need to be stop the world. That's an important point here. So let's dive into our individual collectors. So what I'm trying to do is kind of distilling it at first, and then we'll dive into each of those topics. Okay. The way I'm trying to distill is are they regionalized? Are they generational? Are they compacting? Of course they are, but different kind of compaction. Target pass times and concurrent marking algorithm. So these are the differences that I think I should highlight, and then I'll deep dive into each of them as we go forward. So G1 GC is regionalized, is generational. It does do compaction. Compaction in G1 GC is stop the world, and you have a forwarding address in the header. That's how you realize where it needs to move to. Target pass time for G1 GC is 200 milliseconds. So compared to other collectors, it's the one that gives you better throughput at the cost of latency. And the concurrent marking algorithm in G1 GC is called snapshot at the beginning, and I'll talk more about that soon. Shenandoah is regionalized, is not generational, although it can be generational because it's kind of similar to G1 GC in many concepts. Compaction in Shenandoah is actually concurrent. They use Brooks-style indirection pointer, and I'll talk about that as well. Target pass time is 10 milliseconds or lower, and the algorithm is the same for concurrent marking. It's also snapshot at the beginning. The last one is GC, which is regionalized, is not generational, and it uses concurrent colored pointers. Actually, the core concept is colored pointers, and the compaction is achieved concurrently. Target pass time is also about 10 milliseconds or less, and the way concurrent marking is achieved is by striping. So GC threads get their own stripes to work on, and I'll show more about that here when we deep dive into it. So let's first look at G1 GC. So here are the phases, and I'll keep on adding or deleting phase for each garbage collector. We'll start with the current default, which is G1 GC. So G1 GC has initial mark, final mark, and of course compaction as stop the world pauses. Cleanup is briefly stop the world, but mostly it's concurrent. So during initial mark, you want to mark all this. Remember when I showed the GC routes and I was talking about how do you trace? So during initial mark, that's what you do that. You try to trace from the GC routes, and then you mark those objects at live. Because G1 GC is generational, and because initial mark is piggybacked with a young generation, so if you look at the GC pauses, you will have the young generation pause, and some of the young generation pause will also be initial mark. So because in young generation, you move objects, live objects from Eden to survivor spaces. Now those objects are live, and you just did an initial mark from the root regions. The survivor regions were not accounted for. So that's why you need another concurrent root region scanning phase, where you take these survivor objects as your root objects. So that's why it's called root region scanning. So once basically you marked all your live objects, you marked from the roots basically, so survivor roots and your roots from GC roots. Then you go into something called snapshot at the beginning marking phase, where you build your live object graph, and this is concurrent. After you're done your marking, you want to make sure that the application threads are stopped, so you can traverse any of the live objects that weren't done yet, weren't visited yet. There is also a concept of SATB buffers, which I'll talk about when I'll talk about SATB. But thing to remember is that during final mark, if the SATB buffers have not been drained yet, or if the marking has not been updated with SATB buffers, then that will be done. That has to be absolutely done, because those store the previous value of the pointers. So you need to have that done. So that is achieved during final marking. During cleanup, so if you go back to the regions I had shown, and then there were 2 regions that were full of garbage, they were immediately collected. That is done during cleanup. So you've already identified the live object liveness of these regions, and you know that regions that are full of garbage that can be collected right then. It doesn't have to wait until the Stop the World compaction. And during Stop the World compaction, you're moving live objects from the from space into the to space. And after that, you free the regions that were in your collection set. Stop the World compaction is the easiest compaction, and that's what G1 GC does. It is incremental, so you will see something called mixed collections. It'll have all the young regions and a few of the old generation regions, because G1 GC is generationalized. So let's dive into SATB, and that's how concurrent marking is done in G1 GC. SATB is a logical snapshot. It is called snapshot at the beginning. So basically, at the start of mark, what was live will be marked during the concurrent marking phase. So SATB marking guarantees that if you have any garbage, then that will be known to you. So if at the start of marking the number of objects were garbage, that would be known to you by the end of marking. Okay? So that means all live objects are marked. But because this is concurrent, and because our mutators will mutate, your live graph changes, right? And the way G1 GC handles is, any new objects allocated while the concurrent marking is going on will be considered live, okay? And any reference update will be tracked by the mutators in something called log buffers. And these are your SATB buffers, the log queues, okay? In order to be able to track any reference update, you need a pre-write barrier. So before you make that update, before the write, you need a barrier to guarantee that you're tracking the previous value. So these are all much clearer if you look at these slides, and there's a book as well. So let's look at these pre-write barriers. So basically, if you have an assignment of the form of x.f is equal to y, what you're trying to do is try to save that value, okay, the previous value. So there's an optimization, because you don't have to do this if you're not in marking phase, right? So that is the optimization. So if you are in marking, if marking is active, then you store the previous value into x.f is stored in the previous value register. So if it's not null, then you just enqueue it. So if the previous value was not null, then you enqueue it into the SATB log queue, okay? And that's as simple as that. Again, to read more about it, please do refer the book. The other barrier that G1 GC has, and I have not introduced the concept of remembered set, because it's a concept in itself. So, but just to remember that any old to young references have to be, and old to old references have to be remembered. And then, in order to do that, you have a post-write barrier, okay? So for example, if you have an assignment of the kind object field is equal to some other object, right? Then you would have a write barrier after the reference is updated. And hence the name, it's called a post-write, so it's after write. So the way it filters is, it's just a simple check if it's within the region, right? If it's not, then the barrier is not readed. And if it is, if it equates to 0, then it'll be enqueued into the update lock buffer. So there are two different buffers that I covered. SATB buffer, which is the pre-write. It needs a pre-write barrier enqueued into the SATB log buffer. And this is the post-write for update buffers, which are needed for remembered sets. So anytime you have an old to young or an old to old reference that gets updated, it needs to be remembered, and that's in the update log buffer. Again, to read more, there's the presentation that I did at JVM, JFocus Language Summit, and then there's the book. Okay, so the easiest compaction is stop the world compaction. The way it's done in GCs that do stop the world compaction is by having, in OpenJDK HotSpot especially, having a forwarding pointer in the header. What does that mean? So you have your Java object, which has a body, and it has a header as well. So this is true for all your Java objects, except for the new ones that are going to be introduced here if you went to the talk earlier. So usually your header will have a pointer to an instance class, okay? And basically it's called a class pointer. And then the other part of the header is your mark word. Within the mark word, you have a pointer, and it could be a compressed pointer as well if you're a compressed heap. And then there are 2 tag bits. There are different values to these bits based on if they're locked, unlocked, BIOS lock, but also there's a significance for marking. So during marking, GC workers will compete to install the forwarding pointer of the to space into this pointer space in the mark word. So, so if you go look at the source, you will find that instance class is the VM level representation of a Java class. So the VM has its own representation, and it contains all the information. So you can see that if you go look at the source code. And during mark bits, you will, during mark, the tag bits will be 1, 1. So this is basically, it's a multi-purpose header mark word. And what is important to us for the stop the world compaction is the mark bits will be 1, and the forwarding pointer will be installed in that pointer space. Okay. So now let's go to Shenandoah. What I've done here is I have anything that has changed from stop the world to concurrent, I have it italicized here, and then everything else is highlighted in brown, any new ones. So we have the initial mark, concurrent mark, and the final mark similar to what we saw in G1 GC. There's a very small concurrent cleanup work that's done, and it's only to free the completely free regions. Remember I mentioned about that? That doesn't have to wait for compaction. Shenandoah does concurrent compaction, and it does achieve the same goal, which is to move objects from the from region to the to region, but it is done concurrently. There are also a few other pauses as well as concurrent work for updating references. And then finally, you do concurrent cleanup because now your regions in the collection set are free, right? Because you just moved them to the to space. So the regions in the from space are free, so you free them during a concurrent cleanup. Many of these phases can be piggybacked. So during the next cycle, you can piggyback it accordingly. And that's what, if you look at the paper, that's basically what they cover. There's also a wiki which talks about this, about these phases. I mentioned concurrent marking in G1 GC. This SATB marking is similar in Shenandoah as well. So let's quickly recap the barrier that's needed. So needed for all updates. So what is interesting is it's the same thing. We check for marking is active and we enqueue. Because this is concurrent, nothing changes between G1 GC and Shenandoah. Okay. To read more, it's the same book here. Let's look at how Shenandoah does concurrent compaction. As I mentioned earlier very briefly, it does something called Brooks-style indirection pointer. So we refer back to our Java object. We have the body, we have the header. And what Shenandoah does, it adds an additional pointer here, which is called the indirection pointer. Points to itself if it's not forwarding anywhere. So that's a default state right now. So for every object for Shenandoah GC, it'll have a forwarding pointer. So this is an overhead for every object. Okay. Second thing is that every time you're doing additional work of dereferencing that indirection pointer. Okay. So now let's look at read barriers for the concurrent compaction that we've done. So because we're doing concurrent compaction and mutators are mutating, we need some barriers. So Shenandoah does need read barriers. So it's something simple. So usually you will have reading a field. If you look at an assembly code, it'll look something like this. So you have the get field value. The register RSI contains the address of the object, and then the field offset, so the field that you're reading, is at 10. Okay? But for Shenandoah, because we have the forwarding pointer, the indirection pointer, we would have to change the assembly to look like this. So basically, read the forwarding pointer first, right? So that's why it's 8, -8, and then you get the get field value. So for every get field value in assembly, you will see something like this for Shenandoah, because we have an indirection pointer. To read more about that, here's the link to the paper for Shenandoah. So again, because we're doing concurrent copying, and the way Shenandoah is doing concurrent copying, we need copying barriers as well for writes. Again, the same paper to refer to. In Shenandoah's case, you need the write barriers for all updates, okay? Even primitive types, even locking, just update. When you're locking an object, even that would need a write barrier. What it does is simply checks if you're in an evacuation phase. So basically, if you're trying to do compaction, and if it checks to be true, then it goes down the slow path of checking. And in the slow path, you will check, and this is the write barrier code. You'll check if it's in collection set, and if it's not yet copied, then you'll go ahead and compare and swap. So the way we do compare and swap here is you have a forwarding pointer of the object itself, and then the copy, and then you compare and swap will either be true. That means your mutator is taking care of that. If not, then some other thread took care of it anyway. So that's okay. And the same thing is true if the GC is doing it too. So the same write barrier code is true for GC doing the work as well. So again, the paper that talks more about these. And then, of course, you can look at the code. There are good talks on Shenandoah as well. I have links to that in the further reading section. Let's go to ZGC now. So ZGC also, again, the things are similar to compaction because it's concurrent, so it's in italics there. And then there's a thing called concurrent remap. So that's a new concept. So I've highlighted that here. The couple of things that are different with respect to the previous garbage collectors, concurrent marking algorithm is different. The way it does concurrent marking is by striping. So your GC threads get their own work. So they work in stripes, and they get their own work, and then they can compete. So the way it does concurrent marking is by striping. So your GC threads get their own work. So they work in stripes, and they get their own work. So they get their own work, and then they can compete. So the way it does concurrent marking is by striping. So they get their own work, and then they can compete. So object stealing and stuff like that. So, and then the final mark also does something called weak root cleaning. The phase for compaction is in 3 phases. You have first you prepare for compaction, which means, remember the concept of collection set. How do we know what we need to compact? So that's done in the preparation phase. And then there's also reference processing that is done in the preparation phase. So at the start of compaction, you check for all the roots into the collection set, and then you start doing concurrent compaction. Concurrent compaction is the same concept, move from space to the to space. And then eventually, when you're done compacting, then you want to do remap, which is fix up of all the pointers. So remember, you had pointers, objects that were moved, right? So you want to fix up those pointers because this is the whole background of ZGC is based on colored pointers. So you want to fix up those pointers, and I'll talk more about it when I talk about colored pointers. What is interesting is that concurrent remapping can be piggybacked with concurrent marking. So the first cycle happens, and then the next cycle, you will see concurrent remap happen with concurrent marking. So if you see multiple cycles, so it's kind of piggybacked. So there's an overlap, so to speak. So let's look at colored pointers, okay? So conceptually, it's basically you have metadata that you use, that you store in the unused bit of 64-bit pointers. So for anybody who has studied OpenJDK and compressed OOPS, you would know that if you're using the unused bits of a 64-bit pointer, that means compressed OOPS is not going to work. So this ZGC only works with 64-bit pointers, and also does it work for compressed OOPS. The other concept that I want to introduce is virtual address mapping. So what happens is that you map your virtual address spaces either on x86 into like 3 different multi-mapping, it's called, areas. And some of the hardware like Spark and ARM have some virtual address tagging. So you can actually, you just need to have the virtual space, just one, and just play with the tag bits, okay? And basically, this is how it'll look. You have the object address, and then that would span from 0 to 41st bit. And then you have the unused space, which is 46 onwards to 63. And then you have marked 0, marked 1, which are 2 bits that let you know if the objects are known to be marked, okay? And then you have the remapped, which have the objects been have they been remapped so they're not pointing into the relocation set, which is also known as collection set, right? And then the last one is finalizable. So if the object is reachable only through a finalizer. So that's the concept of colored pointers. Anytime you have any of so basically marked, remapped, or finalizable, you will update those bits, those tag bits accordingly, and that's as simple as that. To read more about this, or to learn more about this, there's a link to the slides here, and it kind of shows you step by step, I think, or at least it talks more about the multi-map feature on x86. So moving on to concurrent marking. So remember I was talking about striping. How does striping help? So having the object, going back to the way the colored pointers work, and we have about 0 to like 42 bits as the addressable area. So we can get up to 4 terabytes, right? So having such big heap considerations. So the best way to do is stripe in the heap. So it's a logical set of stripes. and each GC thread gets its own stripe to work on, and try to minimize the shared states between the GC threads. So you do local work, and you work as fast as you can without having shared states in between. So there is a concept of load barriers, and I'll talk more about that, to achieve concurrent marking. So any loads of non-marked objects need to be detected, and that's why you need the load barriers. And during concurrent marking, you also do concurrent reference processing, which is a new thing for ZGC because most often than not, reference processing is done in parallel. So this is a new concept by ZGC. Thread local handshakes are, again, something that I introduced earlier. So if you remember, going back to the global stop the world pause or thread local handshakes, where each thread will communicate that it's ready to hand over whatever is needed of it and then go back and resume its work. So those are called thread local handshakes. And that's also something that is introduced in ZGC. So let's look at concurrent marking. You have your heap, and you have your GC threads up until like n. So the heap will be divided into logical stripes, such that you have the striped regions for 0 to n threads, 0 to n threads, and so on forth. Each GC thread works with its own stripe until the last thread gets its own stripe as well. And that's basically it. So as long as you're minimizing shared state, you work faster. It's basically the concept of chunking that you do in parallel GC as well. You chunk the heap to do stop the world full GC pause. So that's what it is. Let's quickly look at the barriers. So the first one, read barriers. So this is for references. Remember I mentioned about the load barrier. So load barrier is read barrier. Update barrier is a write barrier, right? So the concept is to update a bad reference to a good reference, okay? It can be self-healing, what does it mean to be self-healing? So if I'm a mutator and I find that I encountered a bad pointer, then I will update it to be a good pointer so that going forward, any other thread that gets to the reference sees that as a good reference. So I am a self-healing mutator is what it means. So self-healing was also some concept that was introduced in Shenandoah as well. So if mutated thread or GC thread could update even in Shenandoah, right? So that's the same concept here. There are two sets of invariants that are introduced. So the first is, so anything that's visible and marked through, visible as marked through, will always be so if they have not done so already. So for example, if I'm a mutated thread and if I don't see that it's marked through, then I will do it. It's my job to repair that as marked through. Okay, so that's one invariant. And then to read, and the second invariant is any loaded value. If you're pointing to the current location, then it should be safely able to access that location. So what that means is that I am responsible of making sure that it's the current and most up-to-date and the correct copy. So that's my responsibility. Again, those are the self-healing invariants that we need to take care of, and that's the basis of these barriers. To read more about it, this is based on C4, which is Azul's continuously compacting concurrent collector. That's why C4. And it's the same concept. Actually, many of the concepts, many of the algorithm improvements in ZGC are from C4 or its predecessor as well. So please read this paper, very, very helpful in understanding these invariants. So let's look at an example. You have object O. So you're loading, so basically you're reading an object reference from the heap. So that's why you need a load barrier, okay? So the way it will be implemented is that so remember the concept is if it's bad, then I want to make it good, right? So if that object O has the bad bit mask, then you take the slow path, and then finally you get the address of object field A, right? To read more, this is the slide deck. So in assembly, object O to object field A would look like this, right? And then you want to check for the bad color. So there's a simple test, check for the bad color, and then if it's zero, not zero, then go to the slow path. Basically, enter slow path, and you either mark, relocate, or remap, depending on what that bad color means to you. So the bad color could be because of marking is not done, or relocation is not done, or remapping is not done. That's why it's bad color. And then you adjust, and then change the value. As simple as that. The concept, so we have, we're pretty close to getting done here. I want to leave some time for Q&A. But quickly talking about concurrent compaction here. The concept of concurrent compaction in ZGC is by using off-heap forwarding tables. Remember, we talked about forwarding tables or forwarding pointers or whatever. That's how compaction basically is done. In G1 GC, you have the header, you throw the forwarding information in the header, and then you move to the to space. In Shenandoah, you add an indirection pointer for every object. That's where the forwarding information is, and move to to space. In concurrent compaction in ZGC, you have an off-heap forwarding table, and that's how it does it very quickly. So you have a load barrier to detect objects pointed into the collection set. It can be self-healing. So for example, if it's not done relocating, then it'll do it. The mutators will take care of that. And basically, you can, as soon as you know that you're done moving from to space, even before the remap can happen, you can reclaim the from space. So not just the physical, but even not just the virtual, which many of them can after a time, but even the physical space can be reclaimed. So the from space is immediately available to be reclaimed and returned back. Okay? To read, to see more details on that, please go ahead and look at the slide deck here. And as I promised for the reading, there are some videos, and there's a good exchange between Gil Tenney of C4 Azul Systems fame and ZGC, which is in the mail OpenJDK list, ZGC's wiki page, as well as the barriers. And we'll go to Q&A, I think about 5 more minutes. Let me. So the first question is, are there any reasons why I would want to stick with CMS? So that would depend on why would you want to stick with CMS. So I'd like to hear more about your use case, and I'll. So could you expand on your use case, please? The person who asked why I want to stick with CMS, could you expand on your use case, please? So there are. Let me explain this. So since JDK 9, CMS has been deprecated. CMS code base is just bizarre, and the GC engineers did not want to maintain it, so they decided to deprecate it. Also, with the introduction of Shenandoah and ZGC, one of the things that we're trying to do is to concurrent compaction, so you don't have to wait for the painful full stop the world pause, right? So there are improvements to the collection algorithm. That being said, yes, Google still has its own version of CMS, and I think Twitter does too. So there are reasons why some people are staying with CMS. It works for them, simply stated, you know. So if that's your use case, and you have a team that doesn't mind being tortured with CMS code base, then please go ahead and do it. But you need a big team like that. Do you know if a Shenandoah GC is being used in real production in the wild? I personally don't, but this would be a good question for Red Hat engineers. I'm sure they have many examples that they know of. If you're active on Twitter, you will know of people at least testing it and running with it and having positive outcomes with it. Okay. How do I choose? Oh, that's a good golden question right there. How do you choose? So Shenandoah and ZGC are targeting low latency environments, right? Shenandoah also has the concept of the strong generational hypothesis and how that works and how it can be more predictable in an LRU case, for example. ZGC by itself does have a lot of overhead in the sense that you have these pauses as well as you're doing a lot of work concurrently, so it can bog down your throughput, right? So when you're looking for just pause time optimization, I would say choose between Shenandoah and ZGC based on your application. If you're looking for throughput, then go with G1GC. I'm going to quickly go to, okay, I'm going to go to the quick, this question, what factors are considered when calculating the expense of a region? So liveness threshold, liveness is the #1 factor. In G1GC's case, you want to see remembered sets and how many are pointing into that region. So for example, if there are a lot of objects that are pointing into, so a lot of references coming into your region, if you move the region, remember you have to update all the references as well. So that becomes very expensive. So expense basically to me and to a garbage collection person or even the garbage collector itself means if I'm moving, because I'm a copying collector and all three of them are, if I'm moving something, how many references do I have to update? It's one of those things. So the more live objects you're moving, you're updating those references, and each of those regions itself will have multiple references coming in. So that's basically what expense means. I think Valhalla things for GC marking. Yeah, so that was the last question here is that Valhalla change things for GC marking. It will, but and also it depends on how you will handle these the objects because remember the way Valhalla does is it'll have just the actual meat, right, and doesn't have the headers and stuff like that. So it does change things a bit. Yes. So if you haven't looked at Valhalla, please go and listen to talks by John Rose. Very interesting upcoming change. So that's all. Go ahead and reach out to me at Twitter. You can, and any questions, you can also email me. It's my first name dot last name at arm. Thank you very much.